Welcome back to ME 760 Engineering Analysis 1. So last lecture we were describing or discussing the eigenvalues and eigenvectors for matrices, and we talked about how to get the characteristic equation for the matrix, and then how to solve, in case of matrices, how to solve this characteristic equation to find the eigenvalues and eigenvector. So today let's just give a brief description of what are the eigenvalues and eigenvectors for some matrices of interest, for example, like the diagonal matrix and the symmetric and skew symmetric, some special cases of matrices. Then we will move on and start a new section for the also chapter number 10, the vector algebra and matrices. We will be discussing the orthogonal matrices. So let's start now. So if we, again, finishing the eigenvalue problem but now for special matrices. So if we look at diagonal matrix, and if A is a diagonal matrix, you knew that it will be A11, A12 up to A1n, and then you will have zeros here, or maybe you will have or you will have A11, A12 up to A1n, and maybe you will have numbers, or you have the zeros here. So the characteristic equation for the diagonal matrix usually will be the determinant of the matrix A minus the identity matrix, as we stated last time, multiplied by lambda, which is the eigenvalue. So in this case, if you substitute here with A minus lambda I, you will notice that you will get the following matrix. This will be the determinant here, and you will have, let's say, so this is all zeros here. So you will get A11 minus lambda 1, and then when you subtract I multiplied by lambda here, then you will get the following format. Let me give you the final results directly. If you just substitute and do the decomposition for the determinants, it will be A11 minus lambda multiplied by A22 minus lambda up to ANN minus lambda. So this will be the determinants. And in order to solve for the eigenvalues, you have to equate this determinant to 0. So in this case, the equation will be just A11 minus lambda multiplied by A22 minus lambda multiplied by ANN minus lambda equal to 0. So what do you think this is? A polynomial, yes? In lambda of what degree? Degree n. So it's a polynomial of degree n. Polynomial of degree n in lambda. So A11 would be equal to what? A1 will be equal to what? Lambda. And A2, lambda 2, A22, and lambda n will be equal to what? ANN. Sometimes you can write this as pi from I equal to 1 to n of aii minus lambda. So pi is just like the summation, but this is for multiplication. So instead of just taking the summation, you will just take the multiplication. Again, as you said, so if you have off-diagonal elements here, if you have those off-diagonal elements, and of course you will have zeros everywhere here under the diagonal and so on, and same situation here. So when you multiply, when you subtract here, let's say a11, a12, and a13 and so on. So if you subtract lambda from here, you subtract lambda from here, and so on. You subtract lambda from a1n minus lambda. When you do the determinant now, this determinant, you will notice that the determinants will give you this multiplication here. So what about the symmetric matrix? Do you still remember what's the definition of symmetric and skew symmetric matrices? What's the definition? What's the definition for symmetric matrix? Yes, A equal to A transpose. This is symmetric. And asymmetric or anti-symmetric or skew symmetric? So any symmetric matrix, any matrix can be written as two components, a symmetric one and a skew symmetric one. So this is symmetric and this is skew symmetric. So you can just write, let's say A will be half A plus A transpose plus half A minus A transpose. So if you add A plus A, half and half is 1, so it will be A, and A transpose half will cancel with minus A transpose, so you do not do anything. Yes? So you can write A as this and this. And this term is the symmetric term, and this term is the skew symmetric term. Yes? Because if you add matrix A to the matrix A transpose, this will be matrix B, for example, or R in this case. Yes? If you try to apply this, you will notice that the A or R equal to R transpose. And in this case, this is the symmetric term. If you compose A minus A transpose, you will call it S. And if you try to look for S and S transpose, you will notice that they are different by a negative sign. So any matrix, you can write it as two parts, a symmetric part and asymmetric part. So let's look at this. 3, 4, negative 1, 6, 0, negative 1, negative 3, 13, negative 4. So I can write this as what? I can write it as 3, 1, negative 2, 3, 1, negative 2, 1, 0, 6, negative 2, 6, 4. So this is the symmetric term, and the skew symmetric term will be 0, negative 5, 1, 5, 0, negative 7, negative 1, 7, 0. So this is A, and I write it as R plus S, and this is the symmetric, and this is the anti-symmetric or skew symmetric. And if you look at the skew symmetric, you will notice that the diagonal is what? Is 0 here. And again, R, you can compose R or write R as what? As A and A transpose plus A transpose. So look for what matrix A and matrix A transpose, for example, and you can write it, for example. Yeah, so the eigenvalues for a symmetric matrix are real, and the eigenvalues for a skew symmetric matrix are imaginary, either imaginary or 0. Those are two properties. So eigenvalues for symmetric matrix are real, and the eigenvalues for real, this is if the real symmetric matrix, and the eigenvalues for real skew symmetric matrix are either imaginary or 0. So for the symmetric matrix, yes, do you have a question?
Why is it positive 4? 3, 4, negative 1, and then 3, 1?
Oh, it's a negative 4, I'm sorry. Thank you. It's a negative 4.
Also, the one on the top? 3, 4, negative 1, and then 3, 1, negative 2, 0, negative 5, 1. Isn't that just addition?
Okay, so 3, 4, negative 1, 6, 0, negative 1, negative 3, 13, negative 4. Then 3, 1, negative 2, 1, 0, 6, negative 2, 6, negative 4. Then 0, negative 5, 1, 5, 0, negative 7, negative 1, 7, 0. So what's your question?
In the top in the middle,
Yeah.
1 plus negative 5 should be negative 4, not positive 4.
Which one? Here?
The
The 4
the
right
value
next to
4.
it.
This one?
Mhm.
Isn't
Okay.
that it just came from the addition of the element from the second column of both?
So you said that this should be negative 1 and this is 5?
Yeah, that would fix it.
So I have to go back and check the numbers. Just check it, but I have to go back and check the number. Maybe I made a mistake when I was writing the. No problem. No problem.
You just put negative 4 the A matrix. First row negative 4 would solve the.
Yeah, or the other way around. You're right. Or if you want, if this is negative 4, so this would be 1, and this would be negative 5.
Okay, that's all.
If this is negative 5, negative 4, sorry. I have to go back and check it again. Let's jump to a new definition here, and we'll define orthogonal matrices. And their transformation. If you remember, a couple of lectures back, we defined the orthogonal vectors. Yes? And if you remember, what are the definition for orthogonal vectors? Huh? Yeah, but orthogonal means perpendicular. So if you take the dot product for, let's say, two orthogonal vectors, will give you what? if you remember the set of orthogonal bases, I, what is equal to? Without looking into the notes. Do you remember this?
Well, yeah.
What's this? Canonical delta function. And this is equal to what? Either 1 or 0. 1 if I equal to j, and yes. So we will define here, this is for vectors. Now, again, for linear vector spaces, the element of the vector space can be matrices. So we'll try to define what do we mean by orthogonal matrix here. So the orthogonal matrix, if we have a non-singular matrix, what do we mean by non-singular? The one that the determinant is not equal to 0. So determinant of A is not equal to 0. If the determinant is equal to 0, the matrix is singular. So a non-singular matrix, if we have a non-singular matrix and the transpose of this non-singular matrix is equal to the inverse of the matrix, we call this matrix orthogonal. So A is orthogonal. The inverse of orthogonal matrix of orthogonal matrix A is also orthogonal. Why? So because if you have, let's say, A inverse, and you take the transpose of A inverse, then when you do that, you can exchange the orders. So this would be A transpose to the inverse of A transpose. And then if this function, if this matrix A is orthogonal, so what's the definition for orthogonality? A transpose equal to what? Equal to the inverse. So in this case, the inverse of a transpose of a orthogonal matrix, the transpose of this inverse is equal to the inverse of this inverse. So this means that the inverse of a matrix is also, if the matrix is orthogonal, is also orthogonal. Did you understand? So the matrix is orthogonal, A transpose equal to A inverse. If the matrix is orthogonal, matrix A is orthogonal, so its inverse is also orthogonal. Why? Because we prove here that the inverse of the orthogonal matrix, the transpose of it is equal to the inverse of it. So again, it is still the same orthogonal. So what's a good property for the orthogonality or orthogonal matrix? So for orthogonal matrix, A transpose multiplied by A is nothing more than A minus 1 multiplied by A, and this is what? Unity. Yeah, identity function, identity matrix. So if you take the determinant for this, you will notice that A transpose multiplied by the matrix A, and this for the properties of matrices and determinants, This is just the determinant of A transpose multiplied by the determinant of A, and this is nothing more than what's the A transpose if this matrix is orthogonal. Yeah, the inverse, but it is also the determinant of the matrix here, A transpose. This will be the determinant of the matrix A multiplied by the determinant of matrix A, and this will be equal to the determinant of matrix A squared, and this will be equal to determinant of I. This will be equal to 1. So if we said that, we have to say here that A transpose multiplied by A is equal to 1 for orthogonality. So far, do you have any questions? Now, there is a good property that we will define now for orthogonal matrices. So if you have a vector, for example, y equal to some operator A, for example, multiplied by a vector x. So you can represent this vector in matrix form as y equal to a matrix A multiplied by a vector x. So this is a real vector. Let's say that this is the real vector, and this is the real vector. Vector y and vector x, and they are related by some transformation. So in matrices, I can write a vector matrix here, a matrix or a vector y equal to a matrix A multiplied by matrix X. So what's the property here of the orthogonality? You will use it in classical dynamics, and you will use it elsewhere also in physics. So this property is orthogonal matrices represent a linear operator that leaves the norm. What do we mean by norm? Length of real vectors unchanged. So again, vector x, vector y, and a matrix here, we will call the matrix as operator. So if we operate the matrix x over a vector, matrix A over a vector x, we will get another vector y. So let's see now, y is a vector, so I can write it as y1, y2, up to yn. So what's y transpose? Yeah, y1, y2, and yn. So I can write it as, instead of a column, I can write it as a what? As a row. So if you want to get the norm of a vector, what's the norm of a vector?
So sum of the squares of all elements.
Huh?
The sum of the square of all elements.
Yeah, but this is the dot product. This will give you the square root of this will give you the norm. Yes, because this is the dot product of y dot y, but this is in real vector space. It's just y dot y. Yes, in Cartesian coordinate. But if you are talking about real vector spaces, usually we put this this brackets here, sort of brackets here, and then if you take the square root of this, this will give you the norm. Norm means the amplitude, the length of the vector. So in order to get this, we have to do y transpose multiplied by y. Why? Because this is a column vector and this is a row vector. You cannot multiply two vectors like column by column or one column by one column. It does not satisfy the matrix multiplication rule. So you have to transpose it so that you will be able to multiply the row by a column. This is y1 up to yn multiplied by y1, yn. So that you will be able to perform the operation, you have to make it y transpose multiplied by y. So in matrix form, what's y transpose? Y transpose what? X transpose A transpose from here. Yes? And what's y? AX. But from the property of orthogonality, what's A multiplied by A transpose? It's the identity matrix. So this will end up with what? X transpose multiplied by X, which is what? In vector space? In vector space is what? The norm of the vector. Yes? So if you have an orthogonal matrix and you operate it over a real vector, what does the orthogonality makes for the vector norm? No change. Because this is the vector, the original vector, and the norm of the original vector, when we operate the original vector by a matrix, it gives us another new vector, it's called y. The new vector, the norm of this new vector is equal to the norm of what? Of the old vector. So the vector norm, or the value of the vector itself, does not change. We will see the geometrical interpretation. This is very nice geometrical interpretation. I will show it to you in a minute here. All of us studied classical mechanics. And we knew that we have, let's assume, a three-dimensional Cartesian coordinate like this. So this is just x, this is y, this is z. Now we have a vector here, r, a vector r, and this is the point here. So it has an x component and it has a y component. And it has an angle here, certain angle. We'll see what's the angle, this angle in a minute here. So now, if we were to rotate the coordinate system with respect to the z-axis, so here is the z-axis here, and this is the x, this is the y, this is the z, and then if I were to just rotate this here, so the new x-axis will be x prime, new y-axis will be y prime, and I rotate the axis by theta. What's the angle between the vector r and the new x prime? I will call this angle alpha. Okay guys? Now, the points are, the vector R has points x and y. But with the new rotated axes, it will have x prime, which is this, all this length is x prime, and it will have y prime, all this is y prime. Of course, if you do just trigonometric analysis or geometrical analysis, you will notice that this is the same theta and this is the same theta, because when you rotate x from here to here, y rotated from here to here by the same angle, theta. So what's x? X is what? R cosine alpha plus theta. And y is what? Sine alpha plus theta. Okay, can you decompose, and let's look also for x prime. What's x prime? R cosine alpha. And what's y prime? R sine alpha. Okay. Let's decompose here the first equation. X equal to R cosine alpha plus theta is cosine alpha cosine theta minus sine alpha sine theta. So this will give you R cosine alpha is what? X prime cosine what? Theta minus, this is what? Y prime sinus theta. Okay, now let's decompose the second one. Y equal to R sine alpha cosine theta plus sine theta cosine alpha, and there is R here. So this will give us what? X prime sine theta y prime, yeah, y prime cosine theta. Y prime here is sine, and y prime here multiplied by cosine. X prime here multiplied by cosine theta. X prime here is multiplied by sine theta. Here it is. R cosine theta is x prime. R cosine, I cosine alpha.
Sorry. You just switched the terms.
Okay.
Yeah, but it's
Okay.
the same thing.
R cosine alpha, R sine alpha is y prime. Okay. What it is? Oh, but this is, sorry, I make a mistake. This is sine theta cosine alpha. And this is sine alpha cosine theta. So this is x prime, so I am right now. Because R cosine alpha is x prime multiplied by sine theta, and R sine alpha is y prime multiplied by cosine theta. I made a mistake when I was decomposing this. So this is alpha plus theta. So you say sine theta cosine alpha plus sine alpha cosine theta. It's whatever you start. So what about z? Do we do anything in the z direction? So z prime should be z. Or z should be z prime. Can we write this in a matrix format? X, y, and z in a matrix format. X prime, y prime, z prime. So Where it is? Here it is. X prime is multiplied by what? So this will be cosine theta, then sine theta, then here is 0. This is sine theta, cosine theta, and this is 0, and here is 0, 0, 1. Yes, guys? So I can write this as what? A matrix A multiplied by the vector x prime, y prime, z prime. Now, can we do the opposite? Can we do the opposite? Yes, we can do the opposite. All what you do is now, instead of solving here, I solve here for what? X and y. Yes? I can still solve for x prime and y prime. Here it is. I will show you how to do it. X equal to x prime cosine theta minus y prime sine theta. Y equal to x prime sine theta minus y prime cosine theta. So if you multiply the first equation here, multiplied by cosine theta, and you multiply by the second equation by multiplied by sine theta. So all what you will do here, this will be x cosine theta equal to x prime cosine square theta minus y prime sine theta cosine theta. And this one will be what? Y cosine theta equal to, y sine theta equal to x prime cosine theta sine square theta minus y prime sine theta cosine theta. If you add those together, what you will get? X cosine theta plus y sine theta equal to x square cosine, equal to x cosine square theta plus sine square theta minus 0, because this cancel out. What's this? 1. So x equal to x cosine theta plus y, x prime equal to y sine theta. If you do the same, but instead of multiplying by cosine and sine switch, you will be able to solve for y what? Y prime. And this will be equal to what, y prime? What do you think? Negative x sine theta plus y cosine theta. So, and of course we will have z prime equal to what? Z, there is no change. So, the three equations for the transformation between coordinates x, y, z and x prime, y prime, z prime are here. So I will leave this matrix here, and then, so what's the new matrix here, guys? X prime, y prime, z prime equal to what? Cosine theta, sine theta, 0 minus sine theta, cosine theta, 0 minus, 0, 0, 1. So this is multiplied by x, y, z. So this is matrix what? This is matrix what? A. And this should be matrix what? Huh? This should be the inverse. Yes? Because this matrix here, A, if you will bring the matrix A here, if you will bring it here, it will be x prime, y prime, z prime equal to the inverse of this matrix multiplied by x, y, z. And this is what we see here. Yes? So this is what? A minus. So you will notice that A minus is nothing more than the transpose of A. Try to transpose this. Cosine, sine, 0. Yes? Cosine, negative sine, 0. There is a negative here. Cosine, negative sine, and 0. I'm sorry for... You should quote it and tell me from the beginning that I commit a mistake. It seems to me that you are not following clearly.
On that equation on top, x and y, the y equation of t plus y.
So y, I think this should be negative and this should be positive, I think. Like this? Or no.
No, the other way around.
So let me
That should be
check. Cosine, negative sine, and sine, cosine. Yeah, there is a negative sign that I did not remember here. So now, when you transpose this, so this will be cosine, negative sine, 0. Look at there, cosine, negative sine, 0. Then this will be sine, cosine, 0. Sine, cosine, 0. Then this will be, the last one will be 0, 0, 1 will be 0, 0, 1. Yes? So the inverse of the matrix is equal to its transpose. So this is what? What definition? Orthogonality. So this transformation is what? Orthogonal. And if you look at the norm of the vector r in the xy coordinates, what's the norm? R is equal to what? X squared plus under the square root. Now, if we want to see this norm in the x, y domain is equal to r, yes? Equal to x squared, y squared. What's x? What's x from here? See what? X prime cosine theta minus y prime sine theta all square plus what's y? It's x prime sine theta plus y prime cosine theta all square. So what's this? When you decompose it, it's the first square, x square prime cosine square theta plus y square prime sine square theta minus 2x prime y prime cosine theta sine theta plus what's this? It's x prime sine square theta plus y prime cosine square theta plus 2x prime y prime sine theta cosine theta all under the square root. So what this will give you? X prime square cosine theta plus sine theta square. What's the value? What's this? 1 multiplied by x prime square is what? And what's this? Y prime square. And what's this? Cancel out. What does it mean? Norm is the same. And this is what the theorem that we just stated a couple of minutes ago. So we said that if you have a matrix that will operate on a vector in real space, the norm of this vector will not change because of the operation that the matrix did on the vector. But under one condition, the matrix should be orthogonal. Yes? Did you see how beautiful they playing with matrices in geometry? So this is very nice, very nice. If you remember when you study relativity, and when you do, for example, coordinate transformation, whether it is rotation or anything like this, or maybe translation or anything like any coordinate change. So if you have a rotational coordinate change, now you will make sure that, okay, my matrix for the coordinate change is orthogonal because of this. The matrix is orthogonal, and the norm for the vector does not change. And this is very trivial here. Do you think vector A, which is this, with respect to x and y, changed when it is with respect to x prime and y prime? So for rotation, the norm for the vector does not change. And because the matrix is orthogonal, it does not change the norm here. So for rotation, the matrix is also orthogonal. But if we look at, instead of rotation, maybe it is translation now, so you'll have x and y, then you move it here by x prime, y prime, so you move it by what? The origin, the new origin now has x naught and y naught. So what's x? X is equal to what? Any point x here. So it will be it will be x naught plus x prime, and y will be y naught plus what? Y prime. So I can write x, y equal to, this is what? 1, and this is what? 1, and this is 1, 1, and this is x prime and y prime. So this is the new matrix now. Just figure out if this new matrix 1, 1, 1, 1 is orthogonal or not. So what's x prime, x minus x naught, and y prime is what? Y minus y naught. So I can write this as what? X prime, y prime equal to what? 1 minus 1, 1 minus 1 multiplied by x and y. So now, yes, go ahead.
When you do that matrix multiplication, you don't get those equations. So
When I do what?
when you do the matrix multiplication at the bottom of the board, you
This one?
x equals x prime plus y prime.
Oh, so we have to change this to be x naught and 0. So this will be what? X naught, maybe. Let's think about it. So if you multiply 1, you do not have y, yes? You do not have y. x1, 1 multiplied by x prime is x1, and this should be 0, and this should be 0, and then you will have to add, when you multiply this, you have to add x dot y dot. So because this will give you x prime, and this will give you 1 prime, and then you will have y naught and x naught. So it's not even. It's not even. So this is, again, this will give you 1, 0, 0, 1, but you cannot plus minus here, x naught, y naught. But you cannot even apply the orthogonality. So it will not work. You cannot even apply the orthogonality. So for the rotation, the matrix is orthogonal, and you can do, the norm is the same. For here, if you have a vector, let's say, from here to here, let's say, so this vector will be, or point x and y, so the point x and y, the vector to point x and y will be different on those two coordinates, if you want to represent it. It's a location of a point, not a vector. A location of the point. But if you take the difference between 2 points, this difference will be the same no matter what coordinate you change or you take. So I will stop here and continue next time Do you have any questions? Thank you.
We have no